who's going to be taking their time with the presentation tonight. Nyan is our rep here in Calgary, and even though the head office is in Ontario, you do have a rep here in Calgary, Nyan, and we can share his contact details with everybody after. So you're at air-cooled chiller alternatives. Hope everyone's in the right place. Chris DeRoche is going to be the facilitator here. He's an experienced application engineer specializing in air-to-water heat pump solutions. So I think you're in the right hands. So I'm just going to turn it over to Chris and let him start the presentation. So thanks again, guys, for your time. I know as busy contractors, it makes for a long day. But we do appreciate your time and hope that you learn a few things going forward. Thanks, Chris. Thanks, Nyan.
Thanks, Lisa. Thanks, Lisa. So again, welcome everyone. Thanks for taking the time to join us, to be with us here today. Just a couple quick housekeeping things. The webinar is being recorded, so just FYI, we'll be distributing a copy to Lisa with MCA Alberta to send it to you guys after the event, and then you'll be able to forward it to anyone in your organization that you might want to show them this. I'm going to turn off my webcam because it seems to always freeze at the most inopportune times. So again, if anyone has any questions as we go through, just keep your microphones muted as we go through it. But if you have questions, for sure, don't hesitate to kind of stop me and ask questions as we go through the presentation. But we'll also have time towards the end to answer any questions you might have as well. So today we're going to talk about air-to-water heat pumps. Mitsubishi has launched a new line of reversible air-to-water heat pumps that provide cooling and heating. So today for the presentation, we're just going to talk about heat pumps very generally, just introducing everyone to the technology. Then we'll also get into a brief analysis on the Alberta climate, look at winter weather data. And then from there, there's a lot of just different applications and information sprinkled in throughout. And then we'll kind of finish off with various examples for 2-pipe, 4-pipe systems, as well as heat recovery examples and so forth. So again, if you have any questions as we go through, don't hesitate to ask. So a reversible air-to-water heat pump, a reversible chiller, these are all words used to describe the same kind of thing. The important thing to remember is that they are an interface between air and water to move heat from one location. So everyone's probably familiar with a typical air-cooled chiller. So an air-cooled chiller will produce chilled water to supply in the building to use in fan coil units or air handlers to cool our buildings. And the way that we're producing chilled water is we're using a compressor and a refrigeration cycle within the machine to move heat from one location to another. So an air-cooled chiller will have these big coils on the machine, and they're located outside. That's a condenser if we're talking about an air-cooled chiller. So that's rejecting heat from the building and basically producing chilled water to send within the building. So an air-to-water heat pump or a reversible chiller, when it's operating in heating mode, is literally just running the refrigeration cycle inside that machine in reverse. So these machines will feature a 4-way reversing valve to redirect the flow of refrigerant throughout the machine, so that the plate heat exchanger inside in cooling mode that was producing chilled water for your building is now producing hot water to use in your building, and it's doing that by switching the condenser to an evaporator. So an evaporator means that we are basically sending refrigerant to that coil on the machine at a temperature that's colder than the outside temperature in order to extract heat from the environment, hence the term heat pump. So you can see it here with a compressor by inputting work. That exchanger is becoming a condenser. We're producing hot water for use in the building and extracting heat using those coils on the machine as an evaporator. So when we think about a 2-pipe changeover system, in traditional systems, those systems usually have an air-cooled or water-cooled chiller and a boiler. So the chiller operates in cooling mode during the summer, and in the wintertime, we switch over and we operate the boiler to produce hot water for a building. So in 2-pipe systems, it's important to keep in mind that any devices inside the building are all getting either hot water or chilled water seasonally. So the idea with a reversible heat pump is, since we have a device that can be a chiller or a heat pump and produce hot water, why don't we use that in our building in the central plant? So here is shown a central plant with heat pumps with an auxiliary boiler. We'll talk about the auxiliary boiler in a couple slides, but the idea is simple. Instead of using the boiler, you have a first stage of heating that's available from the air source heat pump whenever the outside temperatures are compatible with your design in terms of hot water temperature, which we will also get into throughout the presentation. So here's just an example of a central plant with a heat pump, reversible chiller operating in cooling mode during the summer. So shown here, we're supplying chilled water, supply and return throughout the building and various fan coil units and air handlers to cool individual zones. And then in the winter time, whenever we want to produce hot water for those same units, we're switching the heat pump into heating mode, depending on outside air temperature and things like that. And then, of course, the auxiliary boiler is able to run in that system, which does provide a source of redundancy. But essentially, in the wintertime, whenever the heat pump cannot run, you'll run off the auxiliary boiler and supply heated water to those same fixtures inside the unit. So now the question becomes, why would you use an air-to-water heat pump over conventional systems? Well, there's a couple different reasons, but one of the kind of main themes that we're seeing these days is reducing building emissions and reducing greenhouse gas emissions. So of course, whenever you have clean electricity source to run a heat pump as opposed to using natural gas, you can reduce your carbon footprint by using some sort of heat pump technology, especially whenever we talk about hydronic heating. Typically, we use boilers to heat water in our buildings, which is one of the only ways to do it with fossil fuels. The other ways you can do it is with just electric boilers or with some type of electric heat pump. The important thing to remember about the heat pump and the COP is that a heat pump will always be more efficient than pure resistive electric heat because electric heat has an inherent COP of 1. But the other reason why you might want to also look at it is because it has pretty simple integration once you understand the limitations in terms of the heating side of it. It's pretty simple to integrate into the central plant, just like we saw in the previous slides. It's basically a chiller. It can also operate in heating mode. So of course, depending on your HVAC system, you might have some valves to control as part of the BMS. But aside from controls, it's relatively simple integrating that within the building. And now, with greenhouse gas emission reductions being center focus, we also want to look at future proofing our building designs in terms of new builds. And one of the key things with an air to water heat pump is, if you're designing a new building today, that building might only go into operation 3 or 4 years from now. But it's also important to recognize that by looking at some sort of heating capacity, some sort of heat pump, it's important to build in that electrical infrastructure in the building to actually have enough power to run the heat pumps. Because otherwise, these days with retrofits, whenever I go to a job site and look at the mechanical room, if someone's trying to get off natural gas and switch to a heat pump, usually the first thing I'm looking for is what's the available power in the penthouse. For taller buildings, things like that. So that can be a challenge. So, even if the emissions of the Alberta electrical grid aren't as clean as other parts in Canada, it will be improving over the next decade as Canada starts to get control of our greenhouse gas emissions. So certainly using a reversible heat pump in a new design makes a lot of sense in order to build in that electrical heat capacity. And then whenever you look at retrofit opportunities, there's, if you have customers who just have a standard air-cooled chiller and that's coming up for replacement and they're looking at changing that to a similar piece of equipment, there's a lot of good reasons why you might want to have them look at a reversible heat pump chiller instead of that. The cost isn't too much different over traditional chillers, so certainly you're providing a bit more flexibility by making that replacement today. They're still getting the same air-cooled chiller that they would have to produce chilled water in the summertime. But now if they have a heat pump, whenever they would normally shut off that chiller for the winter, they can use that as a first stage of heating when it's practical and efficient to do so based off of local energy prices and also outside air temperature, which we'll get into. So if we look at kind of the government of Canada implementing a carbon tax, there was already a carbon tax that was introduced in 2019, and just recently there was challenges from the Alberta government and the Quebec governments who wanted to opt to do a different type of system like cap and trade. But now that's been kind of over and dealt with in the Supreme Court, and it's been ruled constitutional. So, and you're probably already seeing this on your utility bills for natural gas. You're seeing the federal carbon charge as part of the bills. So the original Greenhouse Gas Pollution Pricing Act was implemented in 2019, which set a price on carbon of $20. So in 2021, in April, the price just went up. So right now the price is about $40 per ton of CO2 emissions. And next year it will go up by another $10 to $50 per ton. In December of 2020, the federal government, this has been a topic of discussion for many, many years, and everyone kind of agreed that, a carbon tax of $50 a ton wasn't really enough to help us actually achieve our goals for climate change reduction. So they actually signaled their intentions to hike the carbon tax up. So right now they're targeting to put the tax up to $170 per ton of carbon emissions by 2030. This isn't formalized into legislation yet, but it's signaling where the direction of the carbon tax will go to support clean energy projects, such as investing in improving our power plants, getting cleaner electricity to use in our buildings, and then also what are we going to do within our buildings? We have clean electricity coming to the buildings now. How can we even further reduce the pollution from any particular building? In terms of new designs for new construction, obviously Alberta climate is a little bit more challenging to design for, but I do a lot of work in Ontario, so a lot of the examples I might have are from Ontario, but we know how to build new buildings now. We know how to build them very well. We have LEED Platinum, we have net zero buildings going up, pretty much the norm. And in the city of Toronto, there's an energy step code kind of mandating lower and lower energy use intensity in terms of carbon emissions over time. But whenever we talk about all of our emissions that we have in Canada, the statistic that's normally floating around there is that about 40% of the greenhouse gas emissions are associated with our buildings. And from that 40% of all the energy that we use in our buildings, about 80% of those buildings represent older, inefficient buildings that need to be retrofitted at some point, whether that's building envelope upgrades, more efficient heating and cooling systems, heat pumps perhaps for domestic hot water instead of burning fossil fuels. So the market is shifting towards some type of clean electric solution to help us reduce our carbon emissions, and heat pumps will definitely be key to that. For today in Alberta, though, it's really more about chillers at this time, although as the power supply in Alberta improves over time, we're going to see more and more heat pump adoption over time. And that's why I wanted to kind of talk about the weather climate difference, because usually I get a lot of pushback about heat pumps, and that's because the market kind of operates one way where we seek a one size fits all solution. Whenever I tell someone I have a heat pump, usually the first question is, what's the cutout of your heat pump? And I tell them it's -15 or -10. And they say, oh, well, in Calgary, our design temperature is -30. So sorry, we can't use that. Call me whenever you have a heat pump that can go down to -30. And there's been a lot of great advances in the technology over the last time, but I'm a firm believer that the days of seeking a one size fits all solution are over. And because it's not really compatible all the time with a low carbon future. So we need to have a little bit of a more holistic approach to actually achieve our greenhouse gas emission reduction targets. So this is a map of Canada kind of showing the major cities throughout Canada. And of course, in British Columbia, this is where they have much milder climate. So it makes a lot of sense for heat pumps. And, in Vancouver, city of Vancouver, starting in 2021, you actually can't use natural gas for space heating or domestic hot water. You need to use some sort of electric heat pump or electric heat solution for the city of Vancouver. But obviously this makes sense because they have a little bit different of a climate. So it's not really a fair comparison between British Columbia and Alberta as an example. But throughout Canada, in the prairies, we have colder temperatures. In Edmonton, the typical design temperature is around -33°C. Calgary, just a little bit shy of -30. And then different parts of the country, it's, all over the place. But, we'll talk more about the heat pump cutout for the air-to-water heat pump that Mitsubishi has available. But this is also representative of most heat pump technologies that are available in the market today if you are seeking a hydronic solution. So, so basically, it's more so about looking at using the heat pump when it makes sense and using an auxiliary boiler whenever the heat pump can't run. But really the message is use the heat pump as much as possible when it's practical to do so. So if we want to look at Calgary, the design temperature in Calgary is -30. The heat pump that we're going to talk about today goes down to -10. So usually with that discussion, our design temperature is -30, so we can't use your heat pump. And that's true, but whenever you look at the weather data, you do find that there are hours where it gets pretty cold. And obviously Calgary and Edmonton are extreme examples of really cold climates in Canada. However, if you look at, this is a histogram, so this is showing just number of hours where you have a certain temperature. So in 1 year, there's 8,760 hours. And of course, if the heat pump can't run below -15, you need an auxiliary boiler. But if we look at the times where we're in the prime heating season, that's good heat pump weather. This is between -10 and +10. We'll talk about why in a couple slides. But even if we just look at the number of hours in Calgary on average for the last 3 years of weather data, there's still 4,600 hours, which is about 53% of the time Calgary spends between -10°C and +10°C. So that's still a huge opportunity for savings for using some sort of electric heat pump as opposed to natural gas if our goal is to reduce greenhouse gas emissions. Similarly, we have Edmonton weather data where it's a little bit more extreme. So you're talking about 16% of the time where it's too cold to run a heat pump. So this is showing times where the temperature is below -15. So an average of 806 hours per year. And then there's times where it's below between -10 and -15. That's another 588 hours. But still, even in Edmonton, it's 4,400 hours still. So 51% of the time that we are spending between -10 and +10. So that's still good heat pump weather. So the temperature ranges in this chart they look awkward, but it's for a reason. And this is to kind of illustrate the operating envelope for a heat pump. So of course, in Calgary, if your design temperature is -30, the heat pump can't run below -30. For this style of heat pump, typically they'll go down to -15 degrees Celsius or 5 degrees Fahrenheit. There is another class of heat pumps. Mitsubishi doesn't have them available, but you can find them on the market. There's another class of heat pumps that are a little bit more optimized for low ambient conditions that can operate down to -20. And some of them can provide a little bit of a warmer supply temperature of 45 degrees. But even then, you still have the same case where, the heat pump cuts out below -20. And your design temperature is -30. So you're still in the same boat of needing some sort of auxiliary heat source. But still, whenever we look at the amount of times, it's about 50% of the year that we can still use a heat pump to produce hot water. So the operating envelope is kind of one of the most important parts to understand about air-to-water heat pumps. And this is basically telling you the relationship between outside air temperature and the leaving water temperature that the machine can produce. So basically, whenever it's -15, the heat pumps can produce usually 40 degrees on the smaller models and 35 degrees on some of the larger models. And nominally, the units can produce about 55 degrees Celsius supply temperature in terms of heating. But you can really only do this between 3 and 10. So, and when we design hydronic systems, in particular for heating, it's usually designers are trying to find just a fixed supply temperature that they know they can maintain at all times. But with the air-to-water heat pump, it is limited by the outside air temperature. So as it gets a little bit colder from 3 degrees, your supply temperature, the maximum supply temperature that the unit can produce, will start to drop off. But still at a minimum, you can supply heat down to -15 outside air temperature and still get a 35 degrees Celsius water temperature. And there's still a lot of really great applications where you can still make use of that. If you want to do heating in the more traditional sense where you have, coils and air handlers, we can increase the size of those heat emitters to have a little bit more capacity to work with lower temperatures. And that's why when you're looking at designing with air-to-water heat pumps, it's really important to understand that you want to design for the lowest water temperature possible. And it may not be practical in all cases, but that's just the main thing to keep in mind if you are looking at applying a heat pump. So for example, if you wanted to use a 50 degrees Celsius supply temperature, that might work in a lot of applications, to use large heat emitters at 50 degrees Celsius, but you can really only supply heat at 50 degrees Celsius or 122 Fahrenheit down to about -5 and as high as about 22 degrees Celsius. If you are able to design for a lower water temperature of 45 degrees Celsius, as an example, And I'll talk about 45 degrees a lot, and that's just one of the reasons is in Toronto, it's a good balance between having a good usability range for the heat pump, being able to use it all the time down to minus 10 degrees, which covers off a lot of the operational hours, and still have a warm enough supply temperature of 45 degrees that you can have good heat transfer in the heat emitters in your building, like air handlers or fan coil units. If you want to go extreme and design for even lower water temperatures, obviously convection units wouldn't be ideal for using a 35C or 95F supply temperature, but certainly if you're designing in-floor radiance systems, these typically operate at lower temperatures anyway. So if you can apply the heat pump to those types of systems, you can take advantage of the heat pump throughout the entire operating range, use it all the way down to minus 15C outside and as high as 40C if you wanted to do heating at that level, and still have the temperature that you need to meet the loads indoors. On the cooling side, I usually don't really talk about cooling too much because in cooling mode, it's a typical chiller that you'd have. Typical chilled water temperature that we have is about 7 degrees is what we use, and about 12 degrees Celsius. So this corresponds to 44 and 54 degrees Fahrenheit. Just note here for the operating envelope, the axes are flipped compared to the ones we were seeing before. So on the y-axis, we have the air temperature, and we have the evaporator temperature on the x-axis here. So really just think about it as a chiller. If you use air-cooled chillers on any of your projects, this might be a product that you might want to take a look at because it still gives you all the same functionality and features that you have with a traditional air-cooled chiller. But now you have the bonus of being able to operate it in heating mode during the wintertime whenever that chiller would normally be shut off. So if we want to kind of consider the design point selection, we know that we have a relationship between outside air temperature and maximum supply temperature from the heat pump. And we also know that we're going to need some sort of auxiliary boiler, either natural gas or electric, to run whenever the heat pump can't run. And this is mainly because natural gas or electric boilers, they're not limited in the same way that the heat pump is in terms of reducing capacity and reducing supply temperature according to outside air. So in the example of Calgary at minus 30 design temperature, if you can design some sort of application using the heat pump down to minus 15, below that you just use the boiler. So it's important to understand that the capacity will also decrease according to outside air, but we'll take a look at that in a couple slides as well. But just in parallel to this, one thing to also maybe think about and keep in mind is we're going to add another secondary y-axis here, and we're going to look at the building space heating load now. We're going to look at the building space heating load as a function of outside air temperature. So we're still looking at this x-axis here and seeing it from minus 30 Celsius up to 40. And we know that typically in the way HVAC systems are designed, we'll have 100% of the heating load occurring at our coldest design day temperature. So in this example, it's minus 30 for the design temperature for Calgary. So we'll have 100% of the heating load from our central plant required at the coldest outside air temperature. And as it gets warmer outside, we have less heat losses from our building. So our capacity that we need as it gets warmer outside will decrease until eventually we don't have a heating requirement, not considering domestic hot water. So that's going to change. It's not necessarily linear. It will follow this kind of trend, but it will zigzag kind of up and down as the loads change in the building, depending on occupancy and things like that. But in general, your load's going to decrease as it gets colder outside. So in addition to this, we're going to also look at hot water supply temperature from the heat pump. So in the example below, I mentioned I was going to talk about 45 degrees Celsius supply, which corresponds to 113 degrees Fahrenheit. And usually, the thinking is that we don't have minus 45. If I tell someone to try to design the heat pump with 45 degrees Celsius water, they say, well, we can't use that temperature in our system. But one way to kind of think about it is maybe you want to use a different supply temperature from the boiler whenever the boiler kicks in and takes over. So in this example here, we're looking at maybe designing for a 45 degrees Celsius supply that lets us run the heat pump continuously down to minus 10. And then whenever the heat pump cuts off and you're switching over to the auxiliary boiler, the boiler doesn't necessarily have to still run at 45. You can supply a higher temperature. And this is kind of how outdoor reset works. And certainly if you're using a heat pump, you can still implement outdoor reset controls on it as it gets warmer outside and change your supply temperature if you don't want to have a fixed temperature. So one way to maybe think about it is, if you're working with engineers, whenever you're doing selections for coils and air handlers that you're sizing for, 60 degrees Celsius, one way to look at it is to maybe do a capacity check with those air handlers, because you have less of a heating load that's required at -10. So maybe you can check the capacity at -10 and see if you still have enough BTUs that you can add into the space using the heat pump. So this is one way to look at it. You can have the heat pump work with the boiler whenever the heat pump can run. They can work at the same time, but you want to be careful about making sure that both devices have the same supply temperature, because the boiler is not limited by outdoor air temperature, but the heat pump is. So for example, if you're designing for a 45, actually a better example would be 50 degrees Celsius supply. The boiler could always do it, but then whenever it goes below -5, the heat pump can't produce 50 degrees anymore. It can produce, 47 degrees whenever you're below -5. So then you'd have some sort of mixing effect with the boiler operating one supply temperature and the heat pump having another, and you might not get that 50 degrees out. One way you could kind of get around that is maybe with controls, you could have the boiler supplying a higher delta T than the heat pump and rely on mixing to have a consistent leaving water temperature of 50 degrees. So again, that's one way that you can look at it. This is a European product, and they do HVAC systems in Europe, designing it around the heat pump. And here, the way we design buildings is, we've always designed typical water temperatures and delta Ts for heating systems, as we've always done it. And now with condensing gas boilers, the go-to is typically, 140 Fahrenheit with a 120 degree return and a 20F delta T. And to be honest, I get challenges times whenever an engineer brings me a design with that higher delta T, and they kind of have the heat pump as an afterthought. They say, oh yeah, well, we've already done this design. How would your heat pump fit into this design? And oftentimes in those cases, it might be a little bit too late, just because of the way the systems are designed. So really, if you do want to look at the air to water heat pump, you'll have the best value if you kind of design it in parallel with the project and design a little bit around the capabilities of the heat pumps, taking that into account to get the best of both worlds. So we talked about the operating envelope and supply temperature changing as a function of outside air. The other thing that changes is we have a reducing capacity according to outside air as well. So in this example, you could have a heat pump size down to -15, supplying 100% of the heat required for the building space heating load. But usually that ends up oversizing the heat pumps in cooling mode. So whenever a manufacturer gives you product ratings at AHRI nominal conditions, that's usually based off 8 degrees Celsius outside air temperature. And usually at 8 degrees Celsius, depending on the building load profile, we'll have less of a heating load that's actually required. So if we looked at the capacity available from a heat pump at nominal conditions, we'd have 140 kilowatts available, but we really only need about 40. So in this instance, this is maybe energy that we could use and dump to domestic hot water if we can design domestic hot water into the system. But oftentimes what we'll do is we'll actually just select a bivalence point where we'll change over. And at the start of the webinar, I said, yeah, the heat pump can go down to -15. But to be honest, in most applications, you probably wouldn't run it down to -15 unless you're doing like condenser loop applications, which we'll talk about later. So oftentimes you can reduce the initial sizing of the heat pump, decrease the cost and the footprint by choosing a smaller size and choosing a point where you're going to change over to an auxiliary heat source anyway. And one of the metrics for this too is you might want to look at your energy pricing and determine a COP where you'll break even between the cost to operate a boiler versus the cost to operate a heat pump. So again, there's a couple different ways that you can do it, but just in principle though, take a close look at how you intend the heat pump to operate within the system and then design the system around it and select your heat pump strategically. Depending on the capacities that you want, as long as you have the temperature satisfied, you could also apply this and look at using the heat pump in parallel with the boiler at the same time too, to kind of maximize the benefit from the heat pump. So this graph here, just in the top corner, just shows the heating capacity relationship according to outside air temperature. And then of course the COP will also decrease as it gets colder outside. So we've talked about the capacity, and the COP will also decrease as it gets colder outside. We've also talked about the operating envelope, how there's a relationship between outside air temperature and maximum supply temperature from the heat pump. So these are things that are important to keep in mind. And the other important thing about air to water heat pumps is in wintertime, since we're extracting heat from the outside, that means we're sending refrigerant to the evaporator coil at a temperature that's colder than what it is outside. And if it's moist or damp outside in the winter, you will have frosting that will occur on the heat pumps. Usually this occurs between about -5 and +5 or so. But basically you'll have frost building up on the coil of the machine, and obviously this inhibits heat transfer. It causes more static pressure drop across the fan on the air side. And basically we need to manage this in the best way possible. So the way that defrosting is done, some of you might be familiar with VRF where they'll go into defrosting cycles. With air to water heat pumps, it's pretty similar. So on the left here is just showing the refrigeration flow in heating mode. So in heating mode, we're producing hot water to use in our building. And we're using that evaporator coil to extract heat, and we get ice forming on that coil. So based off the unit logic, most manufacturers will do kind of simple defrost is what it's commonly referred to as, where it'll basically just look at the evaporating pressure, because you have to keep in mind also that the machine doesn't have eyes. It doesn't really visually know how much frost or ice is built up on the machine. It's monitoring the evaporating pressure and a whole bunch of other parameters on the controller, and it's using that as an indicator to tell you when you have frost and ice built up on the coils. So based off the evaporating pressure, when that decreases, that will tell the unit controller we have frost developing on the coil here, we need to do a defrost cycle. So the way that it does the defrost cycle is you'll actually shut off the pumps on the indoor side, because this is a heat pump. It needs to make hot water to use in the building. Whenever you do a defrost cycle, you're actually just turning the unit into cooling mode. So we want to shut off the pumps on the indoors because we don't want to cool down the water that we've just heated up. And basically with the reversing valve, we just send hot refrigerant directly to that now condenser coil. And we shut off the fans above the condenser coil as well. And we just basically blast hot refrigerant to this coil to try to melt off any frost or ice as quickly as possible so that the unit can go back into heating mode and doing what it's supposed to do, produce heating for the building. So this is how traditional defrosting works. Also, most manufacturers, including the Mitsubishi units, they also have, the technology has been improving. So they have what's referred to as auto-adaptive defrost. And a lot of other manufacturers are offering this now as well. But basically it's, a little bit of a smart defrost. So it's not just looking at simple evaporating pressure, but it's also looking at, outside air temperatures. And you can kind of think of it as a PID loop in between each subsequent defrost cycle. So it's basically learning the weather conditions from that day, and it's learning how harsh the conditions are, and it's tuning the defrost. So I won't get into the details today, but it is optimized to basically allow the countdown timer to shorten or lengthen depending on that day's actual conditions. And it's also using the history from the previous defrost cycles that it's done during that day to kind of optimize it so that you're only defrosting as much as is actually required. So there has been a lot of advancements in the defrost control for these pieces of equipment. But again, most manufacturers are offering both, either traditional defrosting or auto adapting defrost in some form, so that you're only defrosting what's truly required. So now we're just going to talk about, air to water heat pumps, system types, and just basically a lot of examples throughout here. So if anyone has any questions as we go through, don't be afraid to let me know. We can definitely go over it. But really, based off the operating envelope and, understanding how the capacity changes according to outside air temperature, once you have those bases covered and you're applying the heat pump into your project, there's a lot of different ways that you could apply it. And there's a lot of different products that you could use as well. So the NXN series that Mitsubishi has to offer is a 2-pipe changeover. So again, from the examples that we saw at the beginning of the presentation, it's either in heating mode or it's in cooling mode. There's also 4-pipe heat pumps, which are sometimes referred to as simultaneous heating and cooling heat pumps. These machines it's one box with 4 pipes, 2 for hot water and 2 for chilled water. And these machines are also really interesting because they're performing heat recovery within the machine based off the loads in the building. And it's only using that coil as an evaporator or a condenser whenever it's actually required. All other times it's doing heat recovery within the machine. So if we look at just the most basic two-pipe changeover system, this would involve having multiple heat pump units. So again, if we're talking about Alberta, where we would probably today use these as chillers, you'd size them based off the cooling capacity that's required. And then on the right here is just showing in winter, whenever your outside air temperatures are favorable according with your design, you can use the heat pumps in heating mode. And then of course, because we need an auxiliary boiler anyway, due to low ambient cutout, we have the auxiliary boiler that can run when the heat pumps can't run, or if the heat pumps are down for maintenance or things like that. So this is a simple two-pipe changeover system. And this is an example from Toronto, which was actually pretty interesting. It was a new build project, but this would still apply to a retrofit scenario. So it was an 80-ton condensing unit with a remote evaporator that they're looking at. So the engineer came to us pretty late for this project, and they said, "Oh, we heard about your new heat pump. How can you integrate it into this system?" So we said, "Well, get rid of that condensing unit. That was 80 tons. We said, use two 40-ton units." And they said, "Well, what about the heating? What about the heating cutout?" We said, "Well, it doesn't matter. What temperature do you want from the heat pump?" They had already designed the system for about 55 degrees Celsius supply, but working with the engineer, they said, they could live with a 50 degrees Celsius supply temperature according to the energy modeling to still meet the heating loads in their buildings. So we said, okay, that's perfect. Just size 2 units for cooling at 40 tons each. And then on the heating side for their boilers, they had 240 kilowatt boilers, so 280 kilowatts total. So still in this project, they wanted a 50 degrees Celsius supply temperature, which you can achieve at all times down to -5 degrees Celsius. And even whenever you rate that unit at those conditions, nominally, the heat pump was about 150 kilowatts nominal capacity. But at this rating point, it had 107 kilowatts from each heat pump. So heat pump heating, they had 215 kilowatts total capacity available at all times down to -5. In fact, whenever it's warmer than -5, like -3 or even 0, you have even more capacity than 107 kilowatts. But their 100% heating capacity that they needed from the boilers in this case was 280 kilowatts. So we were able to provide 75% of the heating that they needed from the heat pump down to -5. And it turns out that, for 75% capacity, you have more capacity available from the heat pump than what's actually required for your building load typically. But in this example here, they sized the heat pump to provide a capacity of, 215 kilowatts total down to -5. And then below that, they're just switching over to the boiler and running off the boiler. So especially in Alberta, though, if we're talking on the heating side, the maximum supply temperature can be a little bit of a challenge, and this would be one of the reasons why you might want to look at other systems, or if you consider older buildings that require retrofits at some point over the next decade. The challenge with existing buildings, especially if you're talking about older atmospheric boilers that would have been sized for much higher temperatures, like 180 Fahrenheit, which is about 72 degrees Celsius. Usually the challenge with those projects is if you're going to use a lower heat source, even if you were just changing that building to condensing gas boilers that you wanted to operate at 140 Fahrenheit, chances are the heat emitters in the building don't have enough capacity at a lower temperature. So of course, if you did want to implement a full heat pump solution with lower temperatures and change the operating points, you'd have to change the heat emitters in the buildings, which could be practical in some cases if you just have a couple air handling units. If you're talking about a multi-unit residential building where you have hundreds of terminal units or radiators in the suites, that can be more of an invasive retrofit. And for that reason, it might be more preferable to use a cascade system, which is still a heat pump solution, cascading an air-to-water heat pump that we were talking about on the previous slides, and cascading that to water-to-water heat pump. And these are sometimes referred to as energy raisers or a booster heat pump. But these are actually pretty good applications because it solves some of the challenges associated with the operating envelope. In this instance, you would supply a low heating temperature to the evaporator side of the water-to-water unit. But this allows you to basically use the air to water heat pump to the extreme ends of the operating limits. So even though, so in this example, you have about a 30-degree return and a 35-degree supply from the heat pump. Even though, if you look at the point of 10 degrees Celsius outside and you're still doing heating, you could supply a 55-degree Celsius supply temperature from the heat pump if you wanted to. But by keeping it at a lower supply temperature, you're maximizing the efficiency, because for any given outside air temperature from the heat pump, so 10 degrees as an example, the lower the water temperature is, the less hard that the machine needs to work to provide that temperature, and therefore the higher the efficiency is and the better the COP is. So although you could supply a warmer temperature at 10 degrees, you're maximizing the efficiency by maintaining a lower water temperature. So this is the operating envelope for the water to water unit. So we see the air source heat pumps providing that delta T of bringing it from, on the water side now, this is an evaporator, so it's extracting heat. So it's going from 35 back to 30, and then it goes back to the heat pump, gets heated up to 35 degrees again. So this is one really good application. Or if we look at, commercial buildings and water loop heat pump systems, these are pretty good applications in a lot of cases, because you can still do a two-pipe distribution system where you supply kind of condenser loop temperatures of around 30 degrees. And you have water loop heat pumps, and these are water to air heat pumps. So they're basically pulling heat from that loop to provide heating on the air side. Or if they're in cooling mode, they're dumping heat into this condenser loop and providing cooling in the individual spaces. So typically these systems would operate with a boiler and a chiller. So the boiler is just basically a heat injector, and the cooling tower is a heat rejector. And that's typically how these systems work. However, the heat pump works well because if you're going to supply neutral, condenser loop temperatures of around 30 or 35 degrees C, which is around 95 degrees Fahrenheit, this allows you, again, to still use the air to water heat pump throughout the entire operating range, as cold as -15. And then below -15, you just run the auxiliary boiler. So this could be a good application. Just kind of one comment on this is, you might look at the cooling tower and think that the cooling tower would be more efficient to run than a chiller providing chilled water. And, this is why we do energy modeling to find out answers to these questions. But one way you can maybe think about the system as well is this provides maybe an opportunity to downsize the cooling tower and maybe use the reversible chiller in cooling mode only at the extreme temperatures, above 25 degrees Celsius or so, for maybe those abnormal days where it'll get very, very warm. But this presents an opportunity to reduce the size of the cooling tower and use that for the majority of the year, also saving energy that way. But other than that, aside from condenser loop applications, if you want to do, convection units, forced air like fan coil units or air handlers, you'd want to design in the medium temperature zone. So obviously you want to reduce the supply temperature as much as feasible, but obviously there's a balance point in terms of when it's more efficient to use a hotter temperature versus a lower temperature on the pumping side. But still, if we want to look at low temperature applications, water loop heat pump is a great application. Radiant in-floor heating or domestic hot water preheat. Those are also good applications of the heat pump where you can still use them at a very high efficiency at colder temperatures. Taking that same principle for a water loop heat pump system, this is basically how Mitsubishi has a water-cooled VRF system that are typically used with geothermal applications. So whenever you dig a big well to store heat in the ground, and that's good. But one way you can think about an air-to-water heat pump is perhaps a lower cost alternative to a geothermal system. So in this instance, it's basically the same as on the previous slide of a condenser water loop, where these are VRF condensers. And this is a good application with Mitsubishi VRF because there's limitations to the air to water heat pump in terms of the supply temperature, but because you're coupling that to water cooled condensers, and from the condensers, it's refrigerant throughout the building, you're kind of eliminating the operating envelope issue because you're just going to have the heat pump operate at a very low condenser loop temperature all the way down to -15, and all the heating cooling of the individual spaces is taken care of by the VRF system. The other benefit with the VRF system as well is that the VRF system, if you're doing a heat recovery system, you'll recover heat between individual spaces. If you have, a commercial office building where some people have cooling on and other people have heating on, you're going to do heat recovery between those devices in the rooms, and the condensers are only going to actually run whenever you need to basically add or remove heat from the spaces. And the other benefit as well, by relying on the diversity, you could have one floor that's doing cooling dominant, and you could have another floor that's doing heating dominant. So you have water going between these units, and really the heat pump would only kick in whenever it's truly required to either add heat or reject heat from the system in this application. I won't go into it in too much detail, but kind of the other benefits with that system is that you're maximizing the efficiency of the unit in heating mode, because you're choosing a very, very low heating temperature. So, at 0 degrees, you could be supplying, 52 degrees from the heat pump, but you're using almost the coldest temperature that it can produce in heating. So this means that it has the maximum efficiency, which we'll talk about on the next slide. So the heat pump, the air to water heat pump, is operating at its most efficient point. And the same thing on the VRF side, because we're using it with a warmer temperature and heating, we're actually reducing the power consumption of the VRF condenser system as well by 20%. So we're choosing the heat pump to operate at its most efficient point, and we're choosing the VRF system to operate at its most efficient point. So you can see that here on the air to water heat pump side. We talked about 45 degrees Celsius before. This is the coefficient of performance. So for example, if we look at an operating point of 0 degrees Celsius outside, we could have the heat pump supplying 45 degrees to the building to use that in hydronic fan coils, and the heat pump itself would operate with a coefficient of performance of about 2.8. Or on, if we use a 27 degrees Celsius supply, that's how this system was sized. At 0 degrees, the efficiency is 4. So we're increasing it quite substantially in heating mode by looking at the system in this kind of way. Similarly, on the cooling side, the benefits are the same. We're basically stretching out and using the warmest chilled water temperature that the unit can produce. So it's going to produce 15 degrees Celsius leaving water temperature. Whenever the VRF condensers are adding heat to the water and it comes back, the return water temperature might be about 20 degrees Celsius. But again, in cooling mode, the VRF condensers operate at about 30% more efficient in terms of power consumption. So it's, again, in cooling mode, you still have the same benefit. And just looking on the cooling side for the coefficient of performance, if we look at, a milder day where it's maybe 20 degrees, if we were doing 7 degrees Celsius chilled water temperature, we'd have a pretty good coefficient of performance anyway at that point of about 4.5. But with a 15 degrees Celsius supply to work with the VRF system more efficiently, we're also boosting the efficiency of the chiller at about 5.5 COP. So we can increase the efficiency as well that way. So a lot of the systems that we talked about earlier were two-pipe systems, and a lot of you are probably thinking that most commercial buildings are 4-pipe systems that require heating and cooling year-round. So one thing that we've been doing here is trying to investigate how these can be best applied into 4-pipe systems, even though they are 2-pipe units. And what we found was a really good application is actually using 3-way valves at the inlet and outlet of each unit, so that the heat pump can operate in either cooling mode or heating mode. And the 3-way valve position just follows the operating mode. So whenever the heat pump's operating in heating mode, the valve position goes to heating to supply your heating loop. And this unit here can be in cooling mode with the valve position going to the chilled water loop. So you can have some units in heating and some in cooling because they're hydraulically independent here. So this graph here looks a little bit confusing. So the orange line is the building heating load throughout the year, and the blue line is the building cooling load throughout the year. And the red bar shows the heating capacity available from 4 heat pump units when they're all staged into heating. So in January and February, where you don't have any chilled water requirement in the building, you can stage all of these units into heating. So you have 4 units that are available, and you really only need 3 units to meet the capacity in January. Then in March and April, whenever it starts to get a little bit warmer and you do have a little bit of chilled water requirement, you can switch that one of the units into cooling mode, and meet those cooling loads, and then have the other units still staged in heating mode. So in March and April, this is showing 3 units in heating and 1 in cooling. In May, you have a little bit more cooling load, so you need 2 units in heating, 2 in cooling. Then in the peak of summer, so again, this system would be sized for the cooling requirement for the building. So in the peak of summer, whenever you need to stage all those units into cooling, the boiler just makes up the difference on the heating side. And then back into the fall, you're kind of the same trend as on the left here, where you're staging some in heating, some in cooling. So what we did was we actually did energy modeling, and we just started out with Vancouver, Toronto, and Montreal, but we do have plans to start analyzing the rest of Canada after this. But what we did was we said, okay, well, if you have, a standard air-cooled chiller that's up for replacement, rather than replacing it like for like, look at the heat pump system. So how can you best implement this in a 4-pipe system? So basically what we did with energy modeling was we found that we actually only needed 3 units to meet the peak cooling capacity in the peak of summer. And because of the limitations with the heat pumps, you still need to supply an auxiliary boiler to provide heating whenever the units can't operate in cooling. So it was 3 units total, but basically we just did a retrofit scenario. We did the analysis in Vancouver, Toronto, and Montreal. The Vancouver system had a little bit of a higher supply temperature because the design temperature was -7. So we were able to use no auxiliary boiler actually in that system, which is the trend in Vancouver, which is, one of the reasons why that they are a heat pump market. But then Montreal and Toronto, this would be a similar example to what you would see in Calgary as well. If you are going to design a system with 45 degrees Celsius supply temperature, you can do this all the time down to -10. And what we found actually was that you get about in Montreal, you have a 20% reduction in the energy use intensity for the building, but still 42% reduction in natural gas. And the intention of this project was to look at, a low carbon retrofit of a building as part of a fuel switch retrofit. So even in Montreal, which has kind of the harshest climate out of these 3, you're still able to supply a lot of the, reduce a lot of the natural gas. And in Toronto, it was still a 50% reduction in natural gas. And whenever you look at the savings according to carbon tax, that's going to go up to $170 per ton by 2030. Even the prices now, you're talking a substantial reduction in costs. To put it in perspective, in Ontario for a condo building, with the carbon tax, this represents today, or actually, no, sorry, in 2020, it represents about 20% of the pre-tax bill to the natural gas utility Enbridge. So 20% goes towards carbon tax right now. And that's with the carbon tax in its infancy, and it will go up by 2030 to $170 per ton. So there are a lot of reasons why you might want to look at one of these systems today, especially if you have customers coming to you, with chiller retrofits that they need to do. There's a benefit that you can provide to them by using an air-to-water heat pump over conventional chillers if they are looking at air-cooled chillers. Just one of the other benefits also within the 2-pipe units is that, and within this class of heat pumps, is they're usually available with a desuperheater, which allows you to do partial heat recovery. So whenever your main unit is operating in cooling mode and providing chilled water to the building, in heating mode, in cooling mode, you provide chilled water to the building. And then there's another heat exchanger in the unit after the compressor, but before the condenser. And basically, if your storage or recovery loop temperature, if the compressor discharge temperature is hotter than your recovery loop, then the unit logic will allow you to put water through a heat exchanger to recover heat from the unit, because you only want to circulate water through that heat exchanger whenever there's a real opportunity to recover heat. But basically, you're just recovering the desuperheat energy that's required for the refrigeration cycle. You're taking the load off from the condenser fans on the machine and recovering that heat. So nominally, you can recover about 20 to 30% of the unit's capacity with this style of partial heat recovery and get water temperatures as high as 60 degrees. But the caveat to that that's important to keep in mind is that that will be dictated by the load that the compressor is operating at, because the compressor discharge temperature is one of the main inputs for the controls. If your recovery storage loop is lower than the compressor discharge temperature, then you can recover heat. But if your unit's at part load conditions, chances are your if you size the system for 60 degrees C, if you're operating at part load conditions, the refrigerant discharge temperature from that compressor is not going to be higher than 60 degrees Celsius. So that's one thing to keep in mind as well. It sounds good, but you need to take a closer look at it through energy modeling as well. But again, in principle, the controls are simple where you just cycle a valve. So this can be implemented pretty easily to maybe if you do have a 4-pipe system and maybe you're not doing it with 3-way valves for the heat pump, and you do have boilers. So like if we think of in the peak of summer where we're using air-cooled chiller to provide chilled water to the building, usually we require hot water supply as well to do dehumidification with reheat. So sometimes we'll see boilers that are going to operate in the summer anyway. But with this method, rather than using the boiler to produce that heat, you can just pick up energy for free through that desuperheater according to the unit's logic to do that as well. And then so you're basically reducing the work that the boiler has to do and the amount of natural gas that the boiler is using. This is the same principle, but applied to domestic hot water preheat. Just refer to your local building codes and plumbing codes. Legionella is a concern when it comes to domestic hot water. And again, because if you did size the system for 60 degree supply, you'd be able to hit it at peak conditions in cooling. But that happens for a short frequency of time. So as designers, we need to make the evaluation of how much percentage of the time we can recover that heat versus maybe just using a lower temperature that we know we can meet for more of the time, and then maybe use an indirect tank where we're going to preheat domestic cold water and then supply that into our domestic hot water storage tank that's going to be satisfied with a boiler. So that same 4-pipe system that we looked at before, this had through post-processing of that, we found additional savings to basically implement heat recovery for free. And this worked well in the application because we used a lower water temperature in those models anyway. So basically, in the peak of summer, what you would see is 2 or more units operating at peak cooling conditions, 100% loaded. So this means that there's lots of heat to be recovered, and this actually prevented the auxiliary boiler for running for short periods of times or for small loads. And it actually prevented heat pumps from operating in heating mode whenever you could just recover it from the first 2 units as well. So there's still some good benefits to that application as well. Just the last section I want to have is on 4-pipe units, which Mitsubishi will be releasing next year. We're just working with factory to get them to develop the product, but there are other manufacturers. If you are interested in the 4-pipe heat pumps, there are some on the market that you can find. They are good in theory, but really only if you have heat to be recovered throughout the building. If you have a low opportunity to recover heat, like in this example here is just showing a small baseline for heat recovery. You might not want to use a 4-pipe heat pump in this instance because you're going to have the best efficiency when your loads are matched. But in this instance, whenever you have your peak cooling, because in this example, your peak heating is relatively low in the summer, you won't necessarily get the same payback. So maybe a heat recovery chiller instead of a 4-pipe heat pump might be the better application, and size that, and maybe have the reversible heat pump units operate in heating mode to meet any differences in capacities or operate in the shoulder season. So that's maybe one way to look at it. But just to kind of provide some information on 4-pipe simultaneous heating, cooling heat pumps. These will basically have a compressor, but they'll have 2 circuits. So there's a dedicated hot side heat exchanger and a dedicated chilled water heat exchanger. And the coils on the machine that we were talking about before, those in this case of a 4-pipe heat pump are referred to as auxiliary heat exchangers. So if the overall unit is in cooling dominant, it will use these as condensers, or if the overall system is heating dominant, it will use these as evaporators. But other than that, you have dedicated 2-pipe supply and return on the hot water side and dedicated 2 pipes for the chilled water side. And kind of the beauty with this piece of machine as well is that you're basically performing heat recovery within the machine and only using these auxiliary heat exchangers whenever you actually need to extract or reject heat from the system. Whenever it's not using these, it's exchanging heat within the units through refrigerant solenoid valves and really complex control algorithms. But these are usually all handled by the manufacturers as well to control the load staging. So again, in 4-pipe systems, it's not necessarily the COP that we look at. We'll look at the TER instead, and this is the total efficiency ratio, which is really just the cooling capacity plus the heating capacity divided by the power input. And you'll have the best TER whenever your heating and cooling loads are balanced. So this is an example for an office tower in Milan, where when your loads are balanced, you have a total efficiency ratio of about 8. So this means you're getting like basically a COP of 4 on the heating side, and then a bonus COP of 4 basically on the cooling side. But then again, when your loads are less balanced, so that example that we looked at for the heat recovery chiller before, whenever you're providing cooling and doing a little bit of heat recovery, your TER is more like 3.6. So if we compare that to the NXN heat pumps, you know, at about peak conditions, you'd have a COP of about 3. So only really a marginal gain. But again, in British Columbia, they're using a lot of units like this because they have really long shoulder seasons and they require hot water and chill water simultaneously for a lot of the year. So again, it's application specific. But again, 4-pipe are a good tool whenever the loads in your building justify it. But you know, the cost of these machines are substantially more than 2-pipe heat pumps as well. And there's ways that you can still implement good designs with 2-pipe heat pumps instead of using 4-pipe heat pumps, or maybe using one smaller 4-pipe heat pump for the base load and then using 2-pipe heat pumps on top of that as well. I apologize for going over by a couple minutes, but again, just to summarize, you know, best projects where you can find home for this type of equipment, you know, green building certification projects if you want to reduce natural gas consumption, net zero carbon, LEED, or again, according to local building or energy step codes. I have gotten a few requests this year so far from some design consultants in Edmonton looking for suggestions for net zero carbon projects in Edmonton, which surprised even me. But we know it's coming. So, you know, the future will be some sort of heat pump technologies. We're never going to be able to completely eliminate natural gas, and that's okay. It's more about a holistic approach now of using heat pumps or electric heat when it makes sense, and using natural gas whenever the heat pumps can operate. And maybe we want to operate them based off lowest carbon footprint. Maybe we want to operate them off lowest operating costs, but still by implementing reversible heat pumps today, you're providing that flexibility and you're future-proofing your building as well for a low carbon economy. Just the other key message is, you know, don't necessarily think about the heat pump being the star of the system. We always seek one size fits all solutions, but you know, it's again more of a holistic approach. I keep saying that, but I can't really think of any better ways to say it. You know, we're not just putting in atmospheric boilers blasting 180 degrees Fahrenheit now to heat our buildings throughout the year. We got to be a little bit more energy conscious and use our energy in better and smarter ways. Also in ways that work for your clients as well. But there is a pathway to get there, and part of that will be with air-to-water heat pumps. So thank you everyone for your time and for joining us today. I hope you found the presentation interesting and informative. I just have my contact details here, so feel free to take a screenshot or get my contact information. We also have Nyan out in Calgary and our distributor Class Mechanical in Alberta. So if you do want to take a look at it, we'd be happy to take a look at it for you. Sometimes you might do a review and find out that it's a really good project for heat pumps. And other times you might review it and find out that it's not a good application for heat pumps, and that's okay. But you need to start looking at it to see where it makes sense for your business and how it fits in as well. So again, you can reach out to me if you have any questions or anything like that. And of course, if you know, if you need pricing or anything like that, you can contact our friends at Class Mechanical. I apologize for going over, but I'm still available if anyone wants to ask any questions or anything like that.
You guys are being shy. Well, if there's no questions, Chris, I just wanted to thank you very much for your time.
No problem. Absolutely.
And Nyan for setting this up for the MCA members. I'll send out a copy of the presentation once Chris sends it over, as well with Nyan's contact details, so that you have someone here local too. And if you have any